So we've been looking at rate of change. We just looked at instantaneous rate of change. And now when we hear rate of change, we're talking about instantaneous rate of change or the derivative, all meaning the same thing. And so let's look at an example that will kind of tie everything together what we've been looking at so far. So suppose that the amount of water in a holding tank at t minutes is given by the following function: v of t equals 2t squared minus 16t plus 35. And we want to determine each of the following. So is the volume of the water in the tank increasing or decreasing at t equals 1 minute? Okay, so if it's asking me about what's going on there in terms of increasing, decreasing, the rate of change, then that's telling me that I need to look at the derivative. So we want to find the derivative, and it's asking, is the volume increasing or decreasing? So that tells us I want to look at the volume function. So we want to look at the derivative of the volume of the tank at t equals 1. So how can I write that mathematically without having to spell that all out? Basically, I want to find f prime of 1. So we can look at the derivative. I know from looking at down here, it's also going to ask me to find, is my tank increasing or decreasing when t equals 5? So it might be better, and it's not t. I'm sorry, not f up here. This should be a v prime of 1. So I want to find the derivative at multiple spots. So let's actually find the derivative of our volume. So let's first find v prime of t. So again, if we look at the derivative of a function, we're looking at the limit as h is approaching 0. In this case, v of t plus h, I have the function in terms of t instead of x, minus v of t all over h. Okay. So plugging my stuff in, I have, wherever I see a t in my function, v of t, I'm going to first have to start by plugging in t plus h. So I don't know if we want to do this on the side for a little bit, maybe. So let's look at v of t plus h. So wherever we see a t, we're going to put parentheses, and then we're going to go back in and plug in t plus h. So we have 2. I have a t squared, so parentheses squared, minus 16, I see a t there, so parentheses, and then plus 35. So plugging in t plus h inside our parentheses. So now expand and combine like terms. So 2, if we FOILed out 2 plus h times 2 plus h and combine like terms, you would get a t squared plus th, so plus 2th plus h squared. We need to distribute to the negative 16 to each term inside the second parentheses. And so if we do that, we get minus 16t minus 16h. And then let's bring down the plus 35. So now we got to distribute that 2 inside the first parentheses. Oops. And so doing that, we get 2 times t squared, so we got 2t squared. 2 times 2th, so that's plus 4th. Plus 2 times h squared is 2h squared. And then bring down the rest. So minus 16t minus 16h plus 35. So I'm looking to see if I have anything that are like terms, and I don't see any of that. So let's leave it like that. Let's go back in here and plug in what we have. So right now we have v prime of t is equal to the limit as h goes to 0. This whole mess. 2t squared plus 4th plus 2h squared minus 16t minus 16h plus 35. So that was just this piece. So now we want to do minus v of t. So if we do that, minus v of t, all we're doing is we're distributing a -1 wherever we see a term in v of t. So this is equal to negative of our v of t function, which was 2t squared, minus 16t plus 35. So if we do that, we get negative 2t squared plus 16t minus 35. So I'm going to come in here and plug that in. So minus our v of t, so 2t squared plus 16t. Unfortunately, I'm going to have to get rid of this. Plus 35 or minus 35. All over our h. So I know it kind of looks, some of these, they really look ugly at first, but notice that they always clean up really nicely. And so notice the terms start to fall away. And so we have a 2t squared minus a 2t squared. Those cancel out. Notice we have a positive 35 minus 35. Those cancel out. I should have had a t here. And then we have a minus 16t and a positive 16t. Those cancel out. Notice that all the terms that are left have a h in common, so we can factor that out so we won't get that indeterminate form of 0 over 0 when we plugged in the 0 for h. So let's factor out an h while we pull it down. So pulling out an h of 4th, we're left with 4t, plus pulling out an h of 2h squared, we're left with 2h, and then minus pulling out an h from negative 16h, we have minus 16. All over this h. H's cancel. And now we can do direct substitution and plug in 0 wherever we see an h in this function. 4t plus 2h minus 16. So I know my derivative function, v prime of t, plugging in 0 wherever I see an h, I'm going to be left with just that 4t minus 16. Okay, so again, let's go back to what the question said. We want to actually find the derivative of our volume, the rate of change when it is 1 minute. It tells me up here that T is in terms of minutes. And so I'm just going to go in here and I'm going to plug in 1 wherever I see a T in my volume function. And so this is equal to, or V prime of 1 is equal to 4 all times T, so put parentheses minus 16. So 4 minus 16, which is equal to negative 12. So I saw that this is less than 0, which means that it is decreasing. The volume is decreasing. The water is decreasing. At 1 minute. So the next question says, is the volume of the water, the tank increasing or decreasing at T equals 5 minutes? Well, we already found the work where we found the volume, the rate of change of the volume of the whole intake. And we found that V prime of T again was 4T minus 16. So all we have to do here is now plug in 5 wherever we see a T. So this is equal to 4 times 5 minus 16. Well, 4 times 5, that's 20. And 20 minus 16 is 4. And so this is less than 0. I'm not as less than 0, that's greater than 0. And so it tells me that it is increasing. So the volume of the tank increases. At 5 minutes. So is the volume water in the tank changing faster? You think at T equals 1 or T equals 5? So think about it. Is the water rate changing faster when we got this rate of change of 4 at 5 minutes? Or when we're looking at 1 minute when we found that it was negative 12? Well, what do you guys think? 1 minute or 5 minutes? Make them positive. You guys are awesome. So you had mentioned it being at negative 12, and it's because, you know, this is saying that the water in the tank is decreasing negative 12. Okay, what really is that saying? That T equals 1. Well, the rate of change when the time is 1, we're talking about water, is decreasing. And let's see, does it talk about volume? The volume doesn't say what unit, if it was gallons or whatever, but that's decreasing some unit, 12 units per minute, because our time, the variable in the bottom was time. Where m equals 4, this is increasing, but it's not increasing as fast as this is decreasing. And it was asking what what rate of change is faster. So it would be at T equals 1 minute. And I think that was the last question on here. No, it was not. The last question asks, is the volume of the tank ever not changing? And if so, when? So how can we figure out when the volume is not changing? What would happen at that time if the volume wasn't changing? What would we get back? So V prime of t would have to equal what when it's not changing? Well, this would be telling me that my rate of change is 0. So I would just set my derivative equal to 0. And our derivative function was just linear. Gotta grab it really quick. For t minus 16. So we want to look at when is there a time for t minus 16 where that's ever equal to 0? And so if we solve for our time here, we'd add 16, we'd have 4t equals 16, divide both sides by 4 to get t by itself, we get 4. So at 4 seconds, not seconds, minutes, the rate of change stops. Is 0 and not changing. Which really makes sense. We'll find out when our derivative equals 0. That is when we either have a lot of times a max or a min point. And when we saw when t was 1, we saw that our tank, our volume, was decreasing. So it's coming down, right? We saw when t was 5 that it was increasing here. So there has to be some value in between here and here by that intermediate value theorem where it says it has to turn around. So to me, that makes sense. And so down in here somewhere, it's turning around and my graph doesn't look great. And it's actually growing at a slower rate in here at 5. So we might have something that looks like that. Okay, so we're out of time, so let's stop there. We're pretty much done with this definition of the derivative. The next section talks more about the derivative, and it talks about looking at the graph of the derivative. So using this information we know about rate of change at a particular time, and then graphing that derivative function.